All right, so this video is called Related Rates. So just to sum it up, basically related rates deal with the rate of change of two different aspects of the problem that's changing at different rates as time changes. For example, you might have heard an old question like a train heading northbound at 40 miles an hour and a train heading southbound at 2 miles an hour. They're this far apart, and how long will it take for them to meet, and so forth. That's a type of related rate question. So the question we're dealing with right now, the first one is this question. You can pause the video and write this down if you want, because I'm going to erase the screen after I read the problem. But the question is, assume that oil spilled from a ruptured tanker is spread in a circular pattern, whose radius increases at a constant rate of 2 feet per second. How fast is the spill increasing when the radius of the spill is 60 feet? So that's our question. Now, in order to get started with these, I'm going to erase this question just for a moment. I'm going to tell you how I'll begin any of these related rates questions. All right, in beginning, first thing I do is I draw a picture of the problem. So do your best to try. You have to be an artist, but try to draw a picture of the problem. Next, decide what the variables and constants are. Decide what's changing and what letters you'll use to represent what's changing. Also decide what's remained the same throughout this time of what happens in the problem. And finally, create an equation that will allow you to solve the problem. So again, draw a picture, decide what the variables are, and create an equation. I wouldn't start any problem without doing these three things. Let's go back to the problem we talked about. You have it written on your page, so I'm going to use the fact that I have it written down too to start creating our picture. So we got some tanker truck. It has an oil spill. So this is my tanker truck. It's probably an 18-wheeler. All right, this is it. It has an oil spill. It's spilling from the back of this truck. So here we are. And the oil spill is creating a circle for the spill. So this is my oil spill. And what else do we know? We also know that the shape the oil is creating is a circle. So that's pretty useful to remember that's a circle. Because a circle has a radius. So I got some radius R inside of that oil spill. This is what we know. I might make my truck look better. Anyway, so this is what we know. So first thing, I already know my radius. So I'm going to say R equals radius. So that's one variable I know. Another thing is time happening in this question. So T equals time in seconds, because this problem deals with how many seconds it takes. And what else? What other variables might we have here? Oh yeah, area, because the area is changing with time. So area of the circle. So A would be area of circle. All right, so from there we think about, okay, how can I come up with an equation to represent what's happening? Well, we know area of a circle equation, right? We should know. So we should know the area of a circle, and this area is changing with time. So A as a function of T. Area of a circle should be pi radius squared, and the radius is here. So that radius is changing with time. So technically, I could consider that as a function of time because it is changing. So I'm going to call that radius squared R sub T squared. It's R of T squared. By knowing that's a function, it might remind me that I have to use the chain rule to find that derivative at some point, because the rates deal with derivative. That's speed, that's velocity. So ultimately, we look for the derivative of that. So I might remind myself by calling that a function of time by putting the R of T there. All right, so let's go about thinking about this problem. All right, so let's refer back to the question to recall what our goal is in this question. So this is our goal, or this is what we want to answer. So our goal was to determine how fast is the spill increasing when the radius of the spill is 60 feet. So how fast tells me I'm looking for speed or velocity. So that tells me I'm looking for derivative. I'm looking for derivative, and I'm looking for derivative. I'm looking when the oil spill's radius is increasing to 60 feet. All right, so let's actually think about that. I'm about to erase the question now. All right, so we're going to take the derivative of the left side, with respect to time. Take the derivative of the right side, with respect to time. So basically, the derivative of a with respect to time, you can call this derivative of a with respect to time, or you can call it a prime. So the derivative of this piece is just a prime. On the right side is going to be the derivative of r with respect to time, because the radius is also increasing, changing, and the area is also changing. Or you can call it r prime. So I take the derivative of those. You can either call them a prime, r prime, or you can call them these letters dA dt or dr dt. So let's continue. This side should now be a prime of t. That's going to equal to, this is pi times the derivative of this piece. So it's 2 times the radius with respect to time times the radius prime. Because that's chain rule. 2 comes down, subtract 1 from it, so it becomes 2RT, and times the derivative of the inside. So the derivative of RT is R prime of T. So that is the derivative equation. From there, you want to plug in everything you already know about the function. So let's go back to what the function says. I might erase a lot of this. Like I might erase all these variables and a lot of this other stuff because we're running out of space. So do write down everything you didn't already know or everything that's new to you. I'll pretty much write down the whole board because all that's important facts. All right, erasing the screen. All right, so if you go back and reread the question, it said assume that, you go back and look at the question, it says assume that the oil spill from a ruptured tanker spreads in a circular pattern whose radius increases at a constant rate of 2 feet per second. So I know that the radius increases at 2 feet per second, and that's constantly the same thing. So the radius increase is the rate of change of the radius, right? So the rate of change of the radius is r prime. So they told me r prime is 2 feet a second. He told me indirectly what the rate of derivative of r prime was. What they also told me was, they asked me how fast. All right, so they asked me how, I'm gonna write this a little faster. Pause. Asked me how fast is the area increasing? That's the rate of change of the area. So that's a prime. So I'm looking for a prime, and that's what I don't know. And they said how fast is it increasing when the radius of the circle is 60 feet. So they told me what r was. So r is 60 feet, or in this case r of t is 60 feet. So it gave me some important information. So I know r prime, I know I'm looking for a, and I know what r is. Let's take the information and plug it into the problem. So I'm going to erase this. A prime I don't know, so I'm going to leave it as a prime of t. I do know that's pi, this times 2. I know the radius should be 60, and I know the rate of change is 2 feet per second. Now I won't worry about the actual measurements there. Well, I will. I'll keep the measurements there. So that should be 60 feet. You know, in physics, it's really important to have those units correct. This is 60 feet, and this is 2 feet a second. We can get the product here. I'll probably leave pi my answer. You can leave it out, but we'll get that product. And it should be. I'm going to erase all of this stuff over here, so I can write it for the product. So I'm about to erase it if you need it. So this product, a prime of t, should be pi times 240 feet squared a second. Make that look a little bit neater. So anyway, so basically it says 240 feet squared per second, and I just made it look a little neater by calling it 240 pi feet squared per second. All right, so that's it. That's how we do related rates. Notice we drew a diagram, we decided what the variables were, we decided what we're trying to find, and then we found it. All right, I'll give you another one. All right, this is the second example. A 5-foot ladder leaning against the wall, as shown in this figure, 4.12, slips away in such a way that its base is moving away from the wall at a rate of 2 feet per second at the instant when the base is 4 feet from the wall. So I'm assuming right now it's not 4 feet from the wall, it's some other distance at the very beginning. Question is, how fast is the top of the ladder moving down the wall at that instant? So here's the top of my ladder. When this base is sliding outwards, clearly this is going downwards. and we want to know how fast it's going downwards when this is exactly 4 feet from the base of the wall. All right, let's think about first. This is a triangle. So clearly this question deals with Pythagorean theorem because we got a right triangle being formed here. That wall would make a right angle to the ground. All right, so we already have a picture. So our first step of drawing the picture, they're creating one for us. If you're drawing your page, you might want to draw this picture on your own. The next thing we want to do is decide what the variables are. So x is the distance from the wall. So x is the distance from the base of the wall. Y is the height up the wall. And this just represents the ladder. So that's a constant. So the ladder is a constant. You might need that, if not. All right, so the ladder is a constant. Let's think about what's changing with time. As time changes, this is changing with time. So x is a function of time. So x is a function of time. Y is changing with time. So y is a function of time. It says how fast is the top of the ladder moving down the wall. So ultimately looking for y prime. Y prime is what we want to know. It's a question mark. So ultimately looking for y prime. Okay, so I'm going to start erasing all this and start writing up the equation. So let's think what equation we might need. So it's clearly a right triangle. So I would start off with x squared plus y squared equals 5 squared. Because that's Pythagorean theorem, you can find any size to a right triangle. And from there, what you want to find out is we're looking for y prime. So let's find the derivative of the left side for each term. So the derivative with respect to time of the first one, derivative with respect to time of the second one, and the derivative with respect to time of 5 squared. So this would be 2x times x prime, because in this case x is a function, so it's changing with time. So in this case we need to consider the chain rule because x is a function of time. And next one is going to be 2y times y prime, because y is also a function of time. And the derivative of 5 squared is 0. So this is our equation, and now let's go about solving this. Ultimately we want to find y prime. Let's isolate y prime. So right now, pause the video and you isolate y prime. Good practice in how to isolate a certain variable. So pause the video, isolate y prime. I'll tell you what it should be. So you should have found y prime to be negative 2x x prime over 2y. Technically though, you should recognize that those 2's are going to cancel to be 1's. So y prime better written as x times x prime all over y. So we know y prime equals to x times x prime over y. Now let's think about all the stuff we know. What we know is we want to know when x is 4 feet away from the wall, somewhere in there. So yeah, 4 feet from the base of the wall. So that's 4. The rate at which x is changing is 2 feet per second. It's 2 feet per second. And the y value, basically if this was a situation where this is 5, that's 4, well we use Pythagorean theorem, that has to be 3. So the y value at that place has to be 3. So essentially it should be 8 over 3 feet per second. And that's it. So to answer the question, the answer would be, the question was, how fast is the top of the ladder moving down the wall? And the answer would be, the top of the ladder is moving down at 8 over 3 feet per second. The top of the ladder is moving down at 8 over 3 feet per second, or you might say 2.66 feet per second. So that's it. I guess I could have explained this too. Usually I'm a little bit more careful about these feet per second and these whatever units of measure. You might put feet here and feet there, and they would have canceled. And that's why our answer is 8 over 3 feet per second. But yeah, I usually like to be careful with that because it might help you understand the question better. I might help you figure out where you might went wrong if you have that unit of measure in the right place. All right, so anyway, with that being said, that's all I have. Good luck.